Recording is rolling. It is Wednesday, April 16th. So you guys have this packet of thermodynamics puzzles in front of you guys. It's a bunch of questions here. Look at this in a minute. This is going to be a team project. So where it says name, you guys can put multiple names on there, up to 4. You guys can have 2 to 4 names here. You guys got that? 2 to 4 names? Right, you guys are helping each other out on this packet. So the premise of this is I was looking through the thermodynamics questions and materials that I have over the years, and I wasn't completely happy with those. And over the past couple of days, been doing a bunch of thermodynamics information with you guys, a bunch of demos. Okay? And last night I was thinking, well, what do I really want you guys to know from this session? So I was going through the videos from the last 2 days that, of course, I posted to Google Classroom like I always do, and just did a bunch of information that we've gone over. Some of these are demos, some of these are you guys know from the last couple of days. If you've been keeping notes, every few minutes, I'll have you guys pull out some paper and like solve puzzles here or there. Right? So a bunch of those questions show up here. So really, all the answers to these questions are in the videos, or at least how to solve these are in the videos from the last couple of days. And those are, of course, posted to Google Classroom. If you have notes, those can really help you out. So the way we're going to do this is, I think some of these are tough puzzles, even though I should guess exactly how to solve these the last couple of days. Okay? So if you score really well in this, then I'll go ahead and give you the straight grade that you get. Like if you get them all right, then you'll get 100% regardless. Right? But I'm kind of anticipating, I don't know for sure, I just made this last night. I'm kind of anticipating that maybe some of these will be really tough and maybe the raw scores might not be so well, I'm guessing. I don't know. Okay? So if that's the case, then I'll default to this ranking system. So if you and your team members score the best on this packet, even if you miss like 5 questions, but you score better than anybody else for your team, right? Then you'll get 20 out of 20. And if you rank second, then 19 out of 20, third is 18 out of 20, and so on all the way down. So we'll do a ranking system. Now that'll be minimum grade. Again, if you score better on this as well score than that, I'll go ahead and give you the better score. Okay. So you guys got that? We're good? So team challenge. Here, while I got the recording going, let's go ahead and read these questions. Okay, so there's 18 questions here. First question, if you heat a metal ring, how does the hole in the center of the ring itself expand or contract? I think it's the last one you guys saw yesterday. While vacationing in another country, you see the weather report. It's going to be 15 degrees Celsius outside. What is that temperature in Fahrenheit? Oh, and a lot of these I put a note, show your work for credit. So it's a real short equation. Might be on one of these posters that's hanging from the ceiling. Those could be pretty helpful. 2 blocks, each 1 kilogram made of copper. So identical blocks made of copper. Maybe something like this, and that put next to each other in an isolated system, closed system. The colder block has initial temperature of 10 degrees Celsius. The warmer is 20 degrees Celsius. Let's say you come back later, and the temperatures are 5 degrees and 25 degrees. So the cold one got even colder, and the hot one got even hotter. Now that'll never happen, of course, because that would violate what law of thermo? Give you guys some options there. Number 4, what's the only form of heat transfer? We talked about 3 forms of heat transfer. What's the only one that can transmit thermal energy through the vacuum of space? Number 5, which best approximates the pressure for the triple point of water? Ooh, you guys see a pressure temperature phase diagram around? You might see the pressure that's closest to that triple point for water. Okay. Suppose the pressure inside a balloon. Actually, both these next questions, 6 and 7, we start with some balloon. Okay? This is going to probably be ideal gas law. Maybe I'll direct you guys towards. Okay? Now, number 6 says the initial pressure is 1 atmosphere. So let's keep the temperature constant. Let's squeeze on the side of the balloon, get it half its original volume. What's the new pressure inside the balloon? Okay. Of course, include units. Okay, I'm not looking for a number, but a number and also units. Okay. And next question. All right, so sell the balloon. Now, I gave you its initial volume, say 1 cubic meter. Let's keep the pressure constant, but let's warm it up from, say, 20 degrees to 40 degrees Celsius. So we're making it warmer. Right. Now, what's the new volume? You guys think if you heat it up, it's going to expand? But how much? Right. And I gave you a hint as to one answer that it would not be. If you make a mistake, it might be easy to oops. Right. All right, so maybe some ideal gas law on that balloon. What's the ideal Carnot efficiency for a Carnot engine between a hot sink and a cold sink? Between that temperature and that temperature, include units. Actually, you know what? I don't even know why I got that there. Units could just be a percent sign. And if you write this as a decimal, maybe you don't even need any units at all. If I was making this right now, I don't know. It was late last night. Probably wouldn't even include that. Which will cool faster? A kilogram cup of hot coffee with 10 square centimeters of the environment, or the same mass, also 1 kilogram pan of hot coffee with 50 square centimeters open to the environment. Right, so about Newton's law of cooling there. It got a waterfall that's so many meters tall. Right. How much does the temperature of the water rise due to splashing down below? If you're on Earth, you know Earth's gravity field, maybe that might be part of it. I give you specific heat capacity of water. It tells you how easy or difficult it is to raise the temperature of water. Right. That's, of course, the equation from I think that showed up yesterday, I think. If you leave a refrigerator door open all day, then when you return home, the fact that that refrigerator has been operating makes your house overall warmer or colder. Now, the last couple of questions actually are sets of questions. They're in these boxes. So in bold, I have the premise, and then 3 follow-up questions to that premise here. I got 1 kilogram ice cube is pulled out of the freezer. Its temperature is 0 degrees Celsius, but it immediately begins to melt, which might tell you okay, so where it is maybe on a temperature versus heat energy diagram. You can maybe plot a specific point. The specific latent heat of fusion of ice is this value. The specific heat capacity of water is this value. The specific latent heat of vaporization of water, bring it to boil, is this value. Okay? So how much energy does it take to melt that entire ice cube, that 1 kilogram ice cube? Okay. How much energy does it take to bring that same mass of water to a boil? And then how much energy does it take to boil all that away into steam? Include units on all of those for credit. And the last set of questions here is all in a box. So this premise, you got 2 blocks, each 1 kilogram made of copper. So we're back to B right here. Point, something like that. Let's say the cold one starts out 20 degrees Celsius, the warm one is 40 degrees Celsius. And a couple hours later, they reach an equilibrium temperature of 30 degrees, right in the middle. I think that makes sense, right? That'll probably actually happen. I gave you guys the specific heat capacity of copper because they're both made of copper. So that's the material we're working with. Okay. Right. During this process, so here we go. We've got 4 questions here. During this process, how much thermal energy was transferred from the warm block to the cooler block? Show your work and include units for full credit. Next question. What is the increase in entropy of the colder block warming up? And the question after that, what's the decrease in entropy of the warmer block cooling down? And the final question you can get from the previous 2, what's the total change in entropy of the 2-block system? Or you might see that phrase, what's the change in entropy of the universe as a result of that reaching an equilibrium temperature? Of course, on all these last ones, show your work and include units for full credit. There you go. There's 18 questions. Now, my last class, they got, I think, most of the way through this by the end of class. So I think how this is going to pace out is I'll give you guys all class today and all class tomorrow to solve all these puzzles with your teammates. You guys remember 2 to 4 names per packet. And we're going to have this ranking system for minimum grade. Right. And I'll have you guys turn this into the grade tray at the end of class tomorrow.